Oh, hello there. Hey guys, what's going on? Memes here. We're going to be continuing our little computational working sessions. Our most recent notebook, we are on. Oh, I thought I downloaded 14 point. We're on 28. Should be at the Higgs self interaction. Let me share. Hey, Bill, what's going on, my dude? How you doing, my friend? No, I need to make it to some karaoke sometimes. I I am an absolutely horrific singer. You should not allow me to sing. Feel like that should be a crime. Like a Jigglypuff incarnate. That's worse. People can't even sleep. God, imagine that. Jigglypuff was like the original Pokemon ASMR. Going with this up. Let me scroll all the way down, make sure this is the right thing. Oh God, so much random stuff. Okay, I think this is right. Okay, so we didn't get any. I'm gonna have to do further. I'm gonna have to fix some of this stuff because, long story short, we're not really getting that much information. God, yeah, yeah. Don't worry. Most of the stuff is just me, just copying and pasting, and just clicking and rolling up the code. So just trying to show my work, so to speak. Exactly. We show the numbers, and everyone's like, "Oh my God, run away!" All right, it's all right. It's here for posterity's sake. If there's like a 6 hour thing with Professor Stephen Wolf just going through doing things with basically no real commentary, it's like okay, I can at least do this here. Nice white screen. Blinded by the light. There we go. All right. We're at the self-interaction part. Probably share this in the a resident thingies. Where am I? You. Oh God, yes. I'm on a different screen. I'm very dangerous. Heck am I? Copy. Or haven't I? But throw us over in blue sky and we'll throw it in our little niche. The, yeah, thingy called. No, I'm on the big video. It can't bring me anywhere. Uh, computational essay. Throw this little corner in the Wolfram Institute's restricted section. Not actually restricted. I think it's actually a public Discord. Somebody wants to join, just go to the Wolfram Institute YouTube page or their Wolfram Institute. Quick search should bring it up. Barrel roll. God, I'm so bad. Can't even can't even paste the right thing. Doing. Uh, worst YouTuber. Uh, this here. Names. Uh, oh, where? So in the My Theory section, and we just create a little thing. I mean, this can't be right. It's literally going off like a three-digit hunch, and just simplicity's sake. And God, if the measurements keep bearing out, it's going to be ridiculous. But we'll see. Again, not easily falsifiable, but totally falsifiable. We'll just need two or three more significant digits of accuracy. That's all. Ah, through all this past and everything. Close that out over there. Go back over here. Dr. Smith, long time no see. Good to see you. Oh my God. I wish I just looked at some random Discords. I'm like, back in my more debaucherous times. I'm not saying I'm less debaucherous, just perhaps a little bit less publicly. Oh, I'm digging myself a hole again, Dr. Smith. Save me. The good old times. All right, so get back into our mathy stuff, or at least our logic, because that's all mathematics is. It's just a logical thing. Why is there no background? Wait a second. Let me just hold on. Uh, uh, how do I do this? Oh, settings. Oh, layouts. That doesn't matter. Well, okay, the Higgs sulfur interaction. Uh, so to do that, you need to do the calculate the Higgs vacuum expectation value, what we would expect it to be. Perhaps it was at an earlier time, and then at some point, the general gist of what I get is, as the universe cooled, the Higgs field seemed to freeze into place with a non-zero expectation value, and that seems a little strange, but apparently helps to complete the standard model. Hence why somebody that won the Nobel Prize, totally not an effort to sell more books, wrote a book called The God Particle, and I think Professor Kaku ended up doing his own version of that. Uh, okay, so the weird thing, and maybe this shouldn't be that weird, it's literally. This is inverse energy squared. So it's like a really weird number there. You're like, negative giga electron volt speed. What? It confuzzled the heck out of me. But there's a root 2 in there. And if hypothetically we do need to have a minor adjustments on it's a hyperbolic partition equation, rather than doing the Planck mass divide by kilograms, it would be the Planck mass divide by root 2 kilograms. So is there a potential connection? I can't say. That's going to be an exercise left to the viewer or the reader of this eventually to are smarter folks than the author. I think I literally have that written down here. Was it? Uh, yes, yes. Might this have something to do with our apparent three spatial dimensions in which? Oh, long story short, the potential closed form I'm conjecturing for the Higgs vacuum expectation value is three over Gelfand's constant. What the heck is Gelfand's constant? It's literally e, the base of natural logarithms, raised to pi, the constant of curvature. It also happens to be the sum of all even dimensional hyperspheres. How the heck are we dividing that into three? It does have something to do with our apparent three spatial dimensions in which we exist. It's an exercise for the reader and other smarter folks than the author. There we go. Again, a lot of these are just crazy conjectures. That's why I like to say it's stuck in the restricted section. I should probably actually even make sure my audio is working. And that, there we go. Okay, there we go. At least seems to work. I just need to remember if I take one of these AirPods out, it's going to crash everything. Ah, yes, yes. We're literally showing just some dark side right here. All right. Existing in the darkness, just like the little screen thingy that's just a nothing from the never ending story. Always gave me the heebie jeebies. Math there. In full disclosure, we return both a positive and negative value because of the x squared term in our yeah, because squared it could be negative, could be positive. I'm a slightly smaller value, still within our bars of two for the sixth significant digit. And so this value to our original expression for relating the square magnitude of the Higgs mass to the Planck mass, assuming it should be equal to the magnitude of h bar, and we solve for x. I mean, it's giving us the Planck mass right there. How do I eke out some more data? Now, let's see. Actually, is this? Uh, Give this up. Hmm. I mean, it's literally just making up stuff. Undo. Edit, undo. When in doubt, go back. Unbreak things. Let's try this. Oh, really should just log this in. Okay, so plugging that in. I mean, this has 8 significant digits. Be able to eke out at least 7. The other thing, okay, these are just random series. This is just extra information. I'm probably not even going to include just, although one of these is just, that's pretty simple. It's just raised to the root pi. What the heck does that even mean? That's kind of cool. Remember those one for the volume of the figure 8 non, and it wasn't quite right. How much wiggle room do we? Uh, I don't know if that's a whole book of worms or code. All right, we're just gonna do this because it did round before. Can't just write it as computer. Mm, just run it. Okay, we'll take it to our sorry, doing the other thingy there. Yeah. Uh, no, it's right here. Oh, all right, so we need boost Fermi constant. 3, 4, 5, 6. You're going to just roll that up. Not worry about it for the moment. Hold up there. It's not gonna. We're gonna exit out and just go back into it. I'm just gonna take the digits. I know. Terrifying. Sometimes the easiest thing is just quit and restart it. There we go. Share screen. Yeah. Slow that down. So let's get a little bit more tab. But this, I can't believe I can even remember some of these things. Square root of 2, me, that. Oh, I need square root of 2 and the inverse root of the Fermi constant. We raise it to -1, I'll invert it, and then half the inverse square root. Enable dynamics. We actually need to hit it again. There we go. Go compute. All right. Okay, so 1/2 to the 1/4 to the square root. So all results. Okay, this really should be 8 digits. I believe it's 8. I'm just making that up. I'm pretty sure it's been measured really well. 2, 3, 4, 5, 6. Because no, it's the same thing. Hold on. Because it had the same as code out of before. Hold on. Search Fermi. Constant. 1, 1, 6, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 and Fermi cup. I could have sworn this was here the other day. 6, 3, 8, 8. Fine, I'll take it from code data. I could have sworn I saw it on Wolfram Alpha. Hold on. Okay, yeah. Huh. Okay, so it just matches for the first 6 digits. Okay. I was wrong. I thought I just listed all the data. Never mind. This is a measured thing. Let's do that. We're gonna exit out one more time. I know, I know. Now we at least know what we're doing. Uh, oh, bad. We at least know we can make progress now. Let's do that. Let's bring it up one more time. All right. So first off, let's go to code data. Let's share this thing here. Blah blah blah. It's boring, people. No, it's boring. We're literally just gonna pull it right from code data. Not let me minimize it. Let's see. I guess the Fermi thing doesn't. Oh, Fermi constant by h5c to the third. Ooh. I believe this is the reduced Fermi constant. Why is this presenting weird? Because I'm sharing the screen. Hold on. No, I'm just. This isn't how you have the screen because I have it. That's fine. Eh, okay. So we're literally just going to yoink this. Take a picture so it'll last longer. There even any true pictures, bro. 4 digits. 5, 6, 7, 8. Okay. We're going to leverage that. We'll go within the standard deviation. I'd actually calculate something. All right. So what we'll do is, don't mind me with it. My Dragon Ball Super thing. Yes. You got to keep it going. So go back over here. Actual essay. Throw this stuff in. Throw in the digits there. Blah, blah, blah. Self interaction. Okay. So what we're gonna do, gonna move this thing. Insert. Plain text. Gonna move this over here for a moment. Okay. Put this back over here. Now we're gonna do something a little bit higher. Vision. We use the 8 significant digits for the reduced Fermi, then preferred to at the Fermi constant. Hmm, Precision. I should have known that. And try to just anti-correct a mistake. All right. Go grab it. Do this dude over here. There we go. From CoData. Search for Fermi. Go. Well, save as. Yes, yes. What does that say? Yes, the small little things, just because when the notebook does crash, it's make you very sad, especially if you've done a bunch of work. You realize this isn't a bunch of work, but it's minute, but at least puts me back on the right track. So I'm like, wait a second, I'm trying to eke out digits that aren't even. I could have sworn it had the extra couple of digits the other day. Cloud. Go ninja, go ninja, go. Go ninja, go ninja, go. Save. All right. The thing has been done. Hey, welcome, Bill. To see you, my friend. We're just continuing to trek along slowly, slowly but surely. Okay, we're just grabbing the digits, extra digits from CoData. Where did I put? Oh, does it actually just give us? Uh, hmm, hmm, hmm. Uh, we just. Oh, I should just be doing it here. Okay, let's not just break our. We should just be able to. Hmm. You gotta. I need to be thorough. I need to be thorough. Okay, let's do this. Fire. No, I should be do this. Mm, That's we have. Let's do it. 125.376 GEV. And square that thingy. It's seeming quite familiar for some things we've done before, doesn't it? Squaring both terms. So that's going to be 2. We need again square root of 2 in there. We're going to use these digits. These digits here. We're going to need following digits in place. All right. And those digits are times 10 is the -5 GeV raised to the -2. I know, I know. Starts to make my mind wobble. So, since that's an inverse energy, no, so I need inverse square. Raise that to -1/2. Okay, now that we're inverted, an inverse square root, this should be an energy. Now we're dividing an energy squared divided by an energy squared, except with this root 2 factor and that other 2 there, so. Okay. And then this whole thing is square. Let's see what happens. I feel like I should save this. I feel like the computation that will be like, crash. Oh, enable dynamics. Of course. That's it, enter again. Oh, apparently I made a grave error. Hmm, hold on. 10 raised to the -5 gigaelectron volts. All right. Making the inverse square root. Uh, we squared on the wrong side of the brackets, didn't we? That 2 is outside. Okay. That would explain it. Again, user error. Wait. Delete that, and this dude should move into. Into. Onto. Okay. So that 2 is on the out. Around there. Could be. Could be here. Square. All right. Enter now. Oh, a lot. Where is that other root to? Hmm. Okay. Hmm. Where am I getting it from? The whole thing. Energy squared. Okay. And Hmm. Energy, so that's squared. Okay. Squared. So needs to be in one more. Hmm. Now, is it even doing it right? Okay. And then the square. Got that root 2 thingy in there. Oh, it's the inverse of there we go. There we go. All right. So it's in the inverse square of that. I gotcha. Hmm. There we go. Totally user error. Now it should be fine. The inverse square root of that. Oh, that's why it's 2 raised to the 1/4. Okay. There we go. All right. I understand it's the same answer, but we're at least doing a slightly deeper dive. Again, it's limited by the digits up there, but we're going to go back and back calculate them and in the blank math. At least that's the claim. Content. Slowly getting there, one error at a time. Did I just already do that there? Oh wait, this is the old stuff. Hmm. Okay. Wait and delete. Oh, okay. So, so everything is basically the same. What we're gonna do is I'm gonna move this dude down. I learn what I'm clicking at first. Let's just roll up, roll up. All right. And we introduce our above calculated value of the Higgs mass energy to extract out a few more significant digits. Note. Note. There. We use the six significant digits in the database or the eight, 8 digits of data. We are limited to the we are limited to the digits in the numerator. So AE, the mass energy of the uh, there we go. So Higgs mass. I know, I know. Oh, they're just flying all around. Yeah. I'm just looking for patterns. Pattern matching. Dun, dun, dun. +1, okay. Standard deviations. Uh, you don't even have it anymore? Oh, God. There. Oh, God. Higgs, mass of the Higgs, mass of the Higgs, blah, blah, blah. Conjecture ahead, yes. Okay, I'm just copying it again then. That's all I did the first time. Okay, I'm just copying it. Go. All right. Two digits, okay. Save. I know, I know. All right. The Alphonse constant u the pi. It's the sum of all even dimensional hyperspheres. Da, da, da. things, potential reasons for these big things. I know, I sorry. When I put my hand in the way, it probably breaks up all the audios. Okay, here's what we were trying to eke out. All right. So we assume that this is it. We will conjecture that this is true and explore the consequences. In this case, we will leverage this closed form and use our same algebraic expression to bulk calculate. We're doing the Higgs mass here. Okay. Oh God, I said that wrong. Now we're trying to back calculate the Higgs because we're going to assume this is the correct expression. Uh, and more accurate value of the Higgs mass. Now I should be able to. Ah, paste. There we go. Yeah, we had the right thing. I'll save. God. Okay, so what do we need? Ah, here we go. It's a crazy expression. Moved it down, 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 down. Of course I'm doing that wrong. So, all right, so let's do this again. So we're looking for EV, gig electron volts, squared. We need this whole 2 square root 2. Yoink. We don't have all those digits. 3, 6, 7, 8. Right, so -5. EV is 2. So that's that expression there. Is it doing that thing? No. Oh, it's doing the next thing, not the inner thing. Okay, it's okay, it's showing the inside. So there. Here's where we need that inverse square. -1 half. Oh, if. Oh, wait. I didn't even say it equal to anything. Equals 3. Oh, there we go. Trying to solve for x. Say equal to something, right? Yeah. What the heck is it doing there? Hmm? Is it just okay? Maybe this is better. I mean, everything should just cancel. Oh, I need a square. I need that square. To thingy. It's our inner expression that this thing should balance. Gonna throw us into Wolfram Alpha and see where my mistake is. Oh, why? Giga. Elect alt. Write it out. It's taking the V off the dang thing. Okay, there we go. At least skin. Okay, you can work with this. Let's delete this abysmal stuff. I'll get it. Uh, There we go. That's the expression we're looking for. All those things that actually, it totally made me used to like lose my mind. Like, why is this not working? Okay, this expression, we got down to 1, 2, 3, 4, 5, 6, 7. Okay, we got at least 7 digits now, and we can play with that. Okay, uh, little expression. Guys up. Everything won't. Go over there. Where are we? Got this thingy here, this crazy expression. Oh, save as. Takes essay. Or save cloud. Uh, oh, don't mind me. Uh, Save. Hey, there we go. Hey, Quantum Age. Good to see you. Good to see you. We're just continuing to trek away at our little computational stuff and things. The Furby coupling constant is it's apparently a well-measured thing that basically this expression it's inverse energy squared. Um, Apparently, we've known about it, and it's used as a factor to actually compute the Higgs in the standard model. That's why it has a couple of closed forms for it. That's I'm claiming to leverage that unique relationship between the vacuum expectation value. The long story short is I'm conjecturing that perhaps the self-interaction value should be 3 over Gelfand's constant, just because that's a fantastically beautiful thing and it seems to fit the data really well. So what we're doing right now is we're assuming that's true. So now we actually have a constant with many significant digits as we can compute. Um, and if we got this to 8 digits, we should be able to further calculate the value of the Higgs using this relationship and then go back to our original expression where we basically just took the Higgs mass divided into the Planck mass, squared the whole dang thing, and then assume that it should equal to h bar. So we're trying to back calculate additional significant digits for constants on h. Yes, I'm shaking my fist as I'm saying this because we're looking for multiple ways to check. And if we can computationally reduce things in the spirit of the Wolfram Institute, then hey, that seems pretty dang cool. Yeah. Oh, yes. Weather. Thank you. Good catch. Uh, oh, oh, God. I didn't even cleave. Oh, that's not right. Oh, whether or not. Used to express a choice of doubt between two following weather or refers to. Oh, it should be. Oh, all right. It's WH ether or not. There we go. WH ether. Okay, that's right. Thank you. All right. Got all this crazy stuff. Hmm. Some are so much dang different. Oh, we're supposed to be computing the. Shouldn't be that much different. This is. I mean, that's like off by a lot. That it should be a minor deviation there. What did I do wrong? Oh, I'm supposed to. Yeah, I'm supposed to take the inverse root of that. Okay. I need to move this out by one. Um. All right. So within. No, it shouldn't be doing two on that. Do this. Is it keeping that two? Sorry, before. Again, I don't. I often get confused on the question I'm supposed to be asking here. So this. Okay, that's better. Oh, mush puppy. Yeah. Results. There we go. One, two, three, four, five, six, seven. There we go. Dave. Yeah. There. And out there. Yeah. That looks correct. Ooh, open view back up. There we go. All right. All that for one extra significant digit. Will it be worth it? I guess we're gonna have to see. All right. Oh, that's what we're gonna do. Well, anime music just looped. That means we've been going for. So here's what's gonna happen. Uh, yes, not weather. Oh, in the context of the plank light, yeah, that's very interesting. I don't know yet. I haven't spent enough time on that bill as far as because the interesting thing is this whole thing is just based upon just learning that you can computationally reduce alpha to find structure constant to like elementary charge over Planck charge, just square the whole dang expression, bada boom, bada bing. I'm like, oh, it happens to be like the Higgs mass divided by the Planck mass, square the whole dang thing. It looks like the magnitude of H bar. What's going on here? What if I assumed it's true? And those are the things we're conjecturing. At least I'm conjecturing that it should be equal to there, because at that point you could say, well, the squared relationship between elementary charge and the Planck charge is the electromagnetic coupling constant. What if the squared relationship between the Higgs mass and the Planck mass was the mass coupling constant? I mean, Higgs is often attributed with giving at least some mass to some stuff, so I don't know. It's a wild idea. It's a wild idea, and that's why I'm writing a computational essay, and then we'll polish it. We'll get it all beautified. We'll do another community post, get some feedback, and then submit it for any place that would be open to potentially publishing. At least need to go through the rigmarole before I complain about the rigmarole, right? At least I was. So let's do it. Bring up something fun. God, what's a fun thing? Bring let's go on Dad's rant. Um, mm, let's that hasn't been seen. Let's start a little beginning of the Wolf from Institute presentation. That's kind of that's kind of a fun thing. You can see me as I'm in my totally flying slightly more sleep element. Theater mode. Let's go find that. And we'll share this guy over here. Stop that. We will be right back after these messages. We'll be right. Yeah, this is at least kind of fun. There we go. All right. Can everybody see this crazy wheel diagram in the maximally entangled Professor Wolfram?
Yes, yes, we can see it.
Okay, okay. So this was the hero image from the project and everything. So basically, this wheel right here is the current definition of SI. Dugan has brought it to my attention that as of 2030, they're planning on redefining all this in terms of the second. That makes a lot of sense because we got some really good clocks, and you want to have whatever your basis of units are on the things you have the most confidence in. Because with the 2019 redefinition, like I didn't even know. I was working on some stuff and I was looking at some numbers, and I'm like, well, the data listed here is different than what's listed on Codata right now. I had no idea why. Minor investigation, I'm like, oh, they updated this the unit system or the definition of SI in 2019 and they were rolling it out. Hence why certain things were changed, and then you have additional measurements and everything where they're trying to provide the most precise based upon a number of measurements and everything for different constants of nature, which now, for the most part, our units are defined off of here. So basically, we can see here, we'll get into this a little bit further here. Basically, one of the other things that I basically just said out loud what was already defined within the Wolfram Physics Project um, schema, so to speak, was that they have this term here, this zeta. What the heck is a zeta? Well, it's defined within the physics project as elementary energy divided by elementary time, which we have a scaling factor that we're going to get into that's different than this. It's basically G, uh, and it's basically whatever you have that as, you would be scaling Planck units, and that's how they go by it. But the thing is, if you have an elementary energy divided by elementary time, it's going to give you the maximum of power. So it doesn't really matter what that is. So that's why I have Stephen all entangled here and a double cover, so to speak, of some hypersurface here. Um, and there's some interesting little tidbits once we get into this here. But I mean, I could just read through all of this. It's note. This is a new version. The previous version that I know some of y'all had gone through before, some stuff was just wrong. And then when Dugan had messaged me, he actually inspired me to go back, look at these things, go make those corrections. And I actually did add in another section because I kind of feel like I missed the plot, so to speak. The whole main connection was literally sitting right in front of me, and I completely missed it until this past week. So thank you, Dugan.
You're welcome.
Um, so, so basically, our bases in SI, we have 7 base units as of now. So the bases are the meter, which is a unit of length, the second, which is our unit of time, the kilogram, which is a unit of mass, the ampere, the unit of current, the Kelvin, uh, the unit of temperature, the mole, it's the unit that's counting and everything. It is an amount. And the candela, which is luminous intensity, and actually still it has a little bit of a reference to some of the SI units because it does have time in there, but it's ultimately attempted to reconstruct what a human would see for a single candle, which seems kind of crazy. But then again, if you are selling candles and you want a certain luminous intensity, well, you want it to actually be advertised right. Or if you have one of those like 1 million candle power flashlights or something, that's kind of fun sometimes. Just don't look directly into it. Okay. So basically, it's a quick overview of the summary of basically we have a particular factor here, that G factor there, which is basically this little thing over here. If I'm mispronouncing that at all, please correct me. I believe it's capital G, is pronounced. Um, but basically, there's this particular factor that the original estimates were done calculating the estimated age of the universe and using some logarithmic recursion factor and everything. Long story short is I attempted to do something. I was off by 17 orders of magnitude. Xerxes gave me a pro tip at lunch, and then after having my mid-project meeting with Steven, he assigned me homework. So then, while doing my homework, I'm going through and I'm reading over space and time like hypersurfaces and stuff, and we need to have some notion of flux through our hypergraphs here and everything. And I go back and look at the calculation that I had done at lunch after Xerxes gave me the idea, and I'm like, according to Wolfram Alpha, this dimension or interpretation is flux. I'm like, that's interesting. What if I took that seriously? So long story short is I went in, I basically just stripped the dimensions out, which seems like a very reckless thing to do, and then it seemed to replicate a lot of the initial physics project findings within approximately one order of magnitude, which I mean, I wasn't expecting that. Um, but again, this is a speculative connection, but we're going to kind of break it down. All right.
All right.
How the heck did we get here?
Oh, wait, no, wrong
Okay.
thing. No, end the
So
video. What am I doing? There we go. All right. Okay. Uh, I lose myself sometimes. It's like, wait, which is the real me? But the real memes, please stand up. Just sat down. So, all right. Back to our little thingy. Window, Higgs essay. All right. All that work for one significant digit. Let's see what we can do with it. Let's make a count, shall we? Uh, okay. This guy. This was the output, right? Put you in here. I think we can. There, hidden. Yes. Progress. We did this all for the three. Are these both in here too? Me. Me? Mm, definitely hit one thing. No, I didn't undo. Me too. Mm, okay, up there we go. All right. Oh, no, I know. Yields an estimated Higgs mass of. All right, get this expression. Get in. Save. You can tell I've made a bunch of mistakes and then totally confused myself. 6 x squared equals 3 over gallons. I need to put in the digits there. Oh. Okay, so we're ultimately almost done. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. We'll take the seventh digit. Art to rules. What does this do? That's that. All right. Do. Good. Yeah. It will just explicitly state it. All right. So hopefully somebody will help me. So I'm trying computable data. Okay, I'm not going to do computable data. That's far too above my pay grade. This guy. So we're all talking about the same thing. Uh, wrap that up. Jazz up. Okay, so what I want is both the positive and the negative answer, so we have to blow this up again. So just give us our negative answer. Go, wrap you up. Another line of code, throw this here. Positive answer. There we go. Yay. Okay. There we go. Oh, that was a heck of a lot of work. And then again, it's just making a bitch. These guys. All right. There. Okay. Yeah. Undo. Yeah. 3, 4, 5. There is a bit of thing in here for the sake of vision. Shall take to the seventh significant digit. Calculation. All right, so we insert this value into our original expression for relating the squared magnitude of the Higgs mass to the Planck mass. Assuming it should be equal to the magnitude of h bar. All right. Oh, yes, a hallucination. Hallucination. Oh, save as. All right. That's 3-1. Cloud. Grab myself lemon science. I get a little vitamin C, or maybe two. Ah, don't mind me. I'm gonna mute myself while I mukbang for a moment. Okay, I'll only do it when I'm chewing because I can still just ramble on for almost ever. Okay. No, I hate dead air. I'm sorry. Now we're gonna mukbang. Let's see. Or one. Okay. So Planck mass. Wolfram map has digits. Let me just double check. Ultimately, we're gonna need a few more digits. This is share that, share this. All right, the next digit after the 4 is a 3. However, got 2 4 on it. So if it's 1, and again, that 1 probably is not a 0 because it's 1 0 within the error of this. So it seems to be on the lower end. of the current Planck mass, which is an interesting thing. Ultimately, you can nail stuff down. I mean, most of these Planck units are limited our knowledge of gravity because, well, if you just click on the symbol, it's h bar c divided by big G, and we're taking the square root of that. Coincidentally, it seems to be the only Planck unit that just that's taking the square roots that literally just has these out here. So that's kind of cool. So it is technically at the threshold of the error bars. Oh, we're getting bold now. All right. I mean, now facing this last time. I feel like something's wrong here because it's a squared term. Hmm. Well, we are literally just saying all of the same convention. At least put all the stuff we might need, and even if we don't need it there. So basically, what we're doing right here is this was the original expression. The claim is that whatever the Higgs mass is here and the Planck mass is here, whatever those digits are, that squared relationship should equal the magnitude of h bar, which is this. So this right here, the Joule second, is the reference. It's the dimension it's in. So we're literally dividing by one here because this is tuned to this one. It's there. This is an interesting thing. Does that? No, those constants they do have values. So at least if the Planck mass is positive, at least the fifth thing it gives me all the picture roots. We at least want the fifth one. Everything else, nice. Not interested. Nah, there we go. There are one extra digits. That was a lot of work, my friends. Uh, look at dimensions. Ninja this and just throw it in there. Works. Ninja it. Yep, ninja'd. Ninja'd in there. There we go. Well, save. Alrighty. ABC squared, kilograms, blah, blah, blah. All right, equals blah, blah, blah. All right. We return a magnitude for the Planck mass. Uh, then standard deviation is the lower end, the uncertainty. Okay. The is error to four two digits provided codata. Oh, very constant. Okay. These two together. This is personifying these folks. God, there we go. We got our error there. That brings us down to one there. Okay. Again, more digits are required. That's kind of cool. Again, we're trying to narrow down these constants and try to latch onto something and try to back calculate as best we can. Okay, before we had 125.376, and there's a 2 on that 6, so it could go down to about 4, could go down to about up to about 8 in the sixth significant digit. So I mean, we're still within the error bars and everything. So maybe, but we're just trying to hone in on places that might be useful and perhaps give us other clues. So all right, I need to go through and calculate and do the error in the eighth significant digit of that as well. That sounds like something for another day because I think I've had about my fill of this for now. So I know it's not the most exciting thing in the world. As no, I'm really talking. It's essay two. Good number. Cloud. Ta-da. To save. And then we'll publish this and add it to the link below. Publish to cloud. Do. Publish. Copied. All right. I think that's about what we got for now. Oh, what are we trying to AX 1000 binary? What are we trying to figure out with the Planck constant? It's basically H bar. We're attempting to uh the whole claim that basically I'm using inspiration because you can basically just do the alpha structure constant is equal to elementary charge over the Planck charge squared. So the claim is that if we take the mass of the Higgs, we divide it by the Planck mass, we square it, you get a dimensionless number as well. It's about 1.05 times 10 to the minus 34. Um, that times will be the first three digits and correct magnitude of the elementary unit of action, h bar. So I'm conjecturing wildly that perhaps this relationship holds, and it should actually come out to be so basically h bar divide by joule seconds. It's a crazy idea, but I'm like, well, if this is an elementary thing divided by a Planck thing squared that gives you the electromagnetic coupling constant, I don't know, just with words, it seems to line up pretty well with, well, here's an elementary thing divided by a Planck thing squared, maybe gives the mass coupling constant. I don't know. But again, it's conjecture, and some recent measurements seem to increase some credence, let's say, but we'll see. We'll see what happens. So again, it's a crazy thing. Could just be a whole bunch of hogwash, but at least an interesting enough relationship to have me write a computational essay. If you got a better ratio, I'm all ears. Feel free to comment below. But like we're done for today, and we're gonna keep on trekking away, and we'll let the future let's see what's actually going on the best we can. So peace out, everybody. We'll catch you next time.